Hello everyone, my name is Hailey, and in this talk, I would like to talk about my recent paper, Quasi-polynomial time algorithms for quantum games in bounded dimension. This is a collaborated work with Carlo Sparaciari at UCL and Omar Fawzi at Lyon, and also with my supervisor, Berta. The main topic of our work is characterizing quantum correlations of bounded dimension. The motivation to study this topic is that firstly, it is a way to study quantitative advantages of quantum correlations with different dimensions. Secondly, it has a practical importance as well, that it can be exploited as dimensional witnesses in semi-device independent quantum information processing tasks. And lastly, the computational complexity of related problems are not well studied yet. So this is why we studied this topic. Throughout this talk, we'll make use of a tool called nonlocal games. Nonlocal games is one way to mathematically formulate correlations between distant parties. And in this talk, we will particularly consider the case when there are only two players in the game, which is sometimes called two-player nonlocal game. In a two-player nonlocal game, when the game starts, the referee chooses question Q1 and Q2 according to the given question probability distribution pi, and send them to Alice and Bob. Then Alice and Bob have to provide correct answers A1 and A2 to the referee to win this game. The referee checks whether the answers A1 and A2 are correct or wrong according to the given rule function V. After the game starts, Alice and Bob cannot communicate to each other anymore, but they can agree on a strategy beforehand. And in nonlocal games, the advantages of different sets of correlations can be quantified with the maximum winning probabilities achievable using the given correlation set. For example, when Alice and Bob are only allowed to use classical correlations, we can define this classical value omega c, which is the maximum winning probabilities achievable using these classical local correlations. And when they are allowed to use quantum correlations as well, then now we can define this quantum value omega q, which can be calculated with this equation. Here, this rho is the shared, possibly entangled quantum state between Alice and Bob. And this E and D are the measurement operators performed by Alice and Bob respectively. And in this general quantum case, there is no restriction on the dimension of this shared quantum state rho. So this maximization includes the optimization over all possible Hilbert spaces as well. However, sometimes we want to study the case when the dimension of this quantum state is fixed. For example, Alice and Bob might be only allowed to use qubits or qubits. In that case, the relevant quantity is this dimension-bounded quantum value omega qt. And here, the expression is same as this omega q, except that now this Hilbert space H is fixed. So we don't maximize or optimize over it. And in this talk, this dimension-bounded quantum value omega qt is our main topic. Also, it's worth mentioning that nonlocal games can be seen as a generalization of Bell inequalities. For a given specific nonlocal game, which can be represented by a pair of the rule function V and a question probability distribution pi, a Bell inequality can be written as this. So if you're only allowed to use local classical correlations, then any winning probability P must be smaller than or equal to omega c, the maximum winning probabilities using classical correlations. And if omega q is strictly larger than this omega c, it implies the violation of Bell inequality. So we can perform better than the classical case if we can exploit quantum resources. This dimension-bounded quantum value omega qt has a similar application as well. which is called dimension witnesses, and it can be described by this inequality. If the omega qt is strictly smaller than omega q, then we can use this inequality to certify the dimension of your quantum system. If you can achieve a larger winning probability than this omega qt, then it implies that your quantum system must have a larger dimension than this t. And this is why it's called dimension witness. So this is a possible application of omega qt. So this calculating these values are very important fundamentally and also practically. However, these quantities are in general known to be very hard to calculate. Approximating omega c, classical value omega c, with some constant multiplicative vector is known to be NP hard. And approximating this omega q quantum value has recently been shown not to be possible for an algorithm running in finite time. Nonetheless, when we focus on a special class of non-local games, we often can find an effective approximation algorithm for these values. Free game is one example. It is a subclass of non-local games where the choice of the questions Q1 and Q2 is not correlated. In other words, this question probability distribution pi is in this product form. For these free games, quasi-polynomial time approximation scheme for omega c of free non-local games is known. And in our talk, we will also only focus on these free games, and we will try to find an approximation algorithm to calculate this omega qt for these free non-local games. This free game restriction is not a significantly bad restriction in the physicist point of view, since most of non-local games considered in physics are actually free games, including well-known CHSH games. So it is, in a sense, a reasonable restriction. So for this bounded dimensional case, a few semi-definite programming upper bounds have been derived, and some of them demonstrated a good performance for some example non-local games of interest. However, the best known worst case runtime guarantee of these algorithms is exponential in the size of non-local games, and in general, the computational complexity of calculating omega qt is not well studied. So in our work, what we did is we developed new approximation algorithms for computing omega qt of two-player free games with significantly improved analytical running time. We firstly constructed a new hierarchy of SDP upper bounds on omega qt and derived analytical bounds on the convergence speed using quantum definite theorem. And this result gives an upper bound on the computational complexity of computing omega qt of two-player free games. And this is our main result. We can estimate omega qt of a two-player free game within a constant additive error epsilon with a semi-definite program of size this, where A and Q are the numbers of possible answers and questions respectively. And for fixed dimension T, this scales polynomially in Q and quasi-polynomially in A, which means it is an exponential improvement on the previously known algorithms. And for the rest of the talk, I would like to explain each point of this result in more details. And firstly, I would like to talk about how we constructed this new SDP hierarchy. So we did it by drawing a connection to a variant of quantum separability problem. Quantum separability problems are a special type of optimization problems in which the optimization is taken over all quantum separable states. So how did we connect omega qt to this quantum separability problem? First, let's look at the original form of omega qt. Here, I already replaced the question probability distribution pi q1 q2 with this product form, since now we are only considering free gains. Then after a few mathematical tricks, we can rewrite this optimization problem as this longer expression. Here, V is a diagonal matrix whose diagonal elements are rule function V, and this phi is non-normalized maximally entangled state. These new operators E and D are operators in a larger space with larger dimension, and it includes the original measurement operators E and D existed in this original form of omega qt. So this is just another equivalent expression for this optimization problem. But one important feature of this new expression is that now all optimization variables, E, D, and rho, are in the same part here, and they are in the product form. Since product states are extreme states for separable states, we can think of this optimization as optimization over all separable states with respect to the same tripartition as well. Which means that this new expression can be seen as an instance of the tripartite quantum separability problem with additional linear constraints here on the optimization variables. So we found the connection between this omega qt and a variant of quantum separability problems with these linear constraints. However, unfortunately, this connection does not necessarily make the problem easier, as quantum separability problem is also known as NP-hard, and it's very hard to solve. However, there are well-known relaxations for the quantum separability condition called DPS hierarchy. The DPS hierarchy is a converging hierarchy of semi-definite relaxations for quantum separability problem. It exploits the notion of extendable states, which can be defined as this. A bipartite state rho AB is called an n-extendable state if there exists an extension rho AB tensor n, such that any marginal state on any pair of A and B is the original state rho AB, and if it is invariant under any permutation of B registers with respect to A. Extendable states are very useful since, firstly, they are good approximations of separable states, which is related to the concept called monogamy of entanglement. Namely, a state rho AB, which can be shared between A and many different B registers, should not be very entangled because of this monogamy of entanglement. Also, sets of n extendable states form a converging hierarchy of outer approximations for the set of separable states, which means that when n goes to infinity, the set of n extendable states actually converges to the separable states set. Another advantage of extendable states is that they have effective characterization via semi-definite programming, so they can be effectively verified computationally. So using this, we can construct our SDP relaxations, which can be stated like this. So here, with the original objective function for omega qt, we replaced the original product form of optimization variables with this tripartite extension of n extendable states rho. And then we call this quantity nth level of our SDP relaxations. So this first line is nothing but the quantum state condition, semi-definite positivity, and the trace one condition. These two lines describe the extendability constraints coming from the DPS hierarchy. Because this rho is an extendable, they must satisfy permutation invariance. This is now a tripartite state. So now we have two different permutation invariant constraints, and these are these two. And these next two lines, the additional linear constraint existed in our quantum separability problem form of omega qt, which was related to measurement operator C and D. So these are these additional linear constraints on optimization variables rho, apart from these extendability constraints. And this last line is well-known positive partial transpose conditions, which is additionally added to get a tighter bound. So we constructed our new approximation algorithm. And the next step is to see how we derived analytical bounds on the convergence speed of this algorithm using a mathematical tool called quantum definite theorem. Quantum definite theorem provides a quantitative bound on how close any extendable states are to the set of separable states in trace distance as a function of n, the number n, and dimensions. So in a simple picture, it gives an upper bound on the distance between an n extendable state and the set of separable states. However, because our optimization problem is subject to additional linear constraints on the optimization variables, apart from the extendability condition, we need a bit more information than this. So what we need is an upper bound on the distance between an n extendable states satisfying the linear constraints and the set of separable states satisfying the same linear constraints. So the existence of this additional linear constraints makes everything a bit more complicated. And standard quantum definite theorem does not give us this information. So we need, we need an adapted quantum definite theorem. So in our paper, we derived this adapted version of quantum definite theorem called multipartite quantum definite theorem with linear constraints. It can be stated like this. The important part is in this box. So what it says is that if we have this multipartite state rho, so here it's in tripartite state form, but our result can be applied to any multipartite case. So when we have this multipartite state rho, which is n extendable and satisfy this additional linear constraints, we can always find a separable state which satisfies the same linear constraints, and the distance between these two is upper bounded by this quantity in terms of the number n and the systems, the dimensions of quantum subsystems. So for the proof, instead of directly working with the trace distance, we derive the theorem via quantum entropy inequalities. And this is because it is we found it easier with quantum entropies than the trace distance to exploit the unique structure of the correlations existed in extendable states. And this approach was possible because we can convert trace distance to quantum relative entropy via quantum Pinsker's inequality, and further to multipartite quantum mutual information, which has lots of nice mathematical properties such as chain rule. Also, as one of the key steps in the proof of the quantum definite theorem, we derived an informationally complete measurement which minimizes the loss in distinguishability relative to quantum side information, which we think may be of independent interest to some people. You can find the details in our paper. But finally, using this adapted version of quantum definite theorem, we can find an upper bound on the accuracy of our STP relaxations, which is given as these inequalities. And this straightforwardly gives the main result of our paper, the computational complexity of calculating omega t of a two-player free game. We can estimate it within a constant additive error epsilon with a semi-definite program of size this, where A and Q again denote the number of possible answers and questions respectively. For fixed dimension T, the complexity scales polynomially in Q and quasi-polynomially in A. And these results can be seen as a quantum extension of quasi-polynomial time approximation scheme for this classical value omega c for 3 non-local games, which I mentioned earlier in this talk. So for conclusions, as we just saw, this is the main contribution of our work. And this is an exponential improvement on previously known approximation algorithms for omega qt in terms of worst case runtime guarantees. For an open question, it would be interesting to look at whether the t dependence of our result is optimal. As there exists a matching hardness result in the classical limit when t equals 1, we can deduce that the A and Q dependence of our result is optimal. However, it does not tell us anything about the optimality of t dependence. So it might be worth exploring some other methods as well, for example, epsilon net-based methods to see whether this t dependence is optimal or not. We would also like to remark that our result is consistent with the recent hardness result for omega q, as the complexity diverges when t goes to infinity. This is the end of my talk. Thank you for listening. And if you have any questions, please feel free to ask me via email. Thank you.